Alright, folks, welcome to the thrilling conclusion of spooky correlation. Let's talk about some additional correlation information. One factor in correlation, just like with many other statistical analyses, the more cases you have, the greater the likelihood that you'll find statistical significance in your relationship. The other important thing to remember is that correlation coefficient, if you're doing Pearson R or any other coefficient, the value of that coefficient is not the percentage that those two variables are related. Okay, that requires a little bit an additional calculation, which is to take that correlation coefficient and square it. We call that R square. And that essentially is a measure of the common or shared variance between those two variables. Or we can think of it as the proportion of the variance in the dependent variable that is predictable from the independent variable. Finally, we might find that we need to use different calculations, different coefficients for different types of data, nominal, interval, ordinal, and ratio, and different shapes of the data, and sometimes based on the number of respondents. You can look in your textbook on page 211. It goes into detail about these. And then really, finally, the restriction of range can lead to erroneous conclusions. What is restriction of range? Let's take a look at that now. Let's consider this research question. Is admission test score, like SAT or GRE, related to a student's college GPA? Here's a plot of some variables. We've got admission test score along the x-axis from 400 to 800, and we've got first year GPA along the y-axis from 0 to 4.0. And take a look at these dots and how they're scattered across this relationship. What kind of relationship, positive, negative, or no difference, no relationship, do you see here? And in addition, how strong is that relationship? I see a positive relationship that's not very strong. Okay? But let's talk about restriction of range here. First, let's look at the non-restricted range. We have the full range of values from 400 to 800. Okay, and we've got scores that assume a wide range of GPA and admission test score. What would happen if we only, say, looked at these variables in the top corner? Only those who had among the highest admission test score. These are the ones in red, these red squares. Let's say maybe this is a highly competitive UC school or private school like Harvard or something like that, where students who get accepted tend to only be pulling from this top end of the admission test score range. If we only considered the scores in the top quadrant, this restricted range, we might find a very different relationship, where very slight positive, but probably would be below our 0.35 threshold for determining if a coefficient is small or moderate. So by selecting only the top end of these scores, we've restricted the range so much that we don't have the ability to see this full relationship. That's restricted range. So whenever you're looking at a correlation coefficient, you want to ask yourself if the data have been restricted in range to some way. And is that why you might be finding a counterintuitive finding? Alright, so thus far, we've been talking about the first type of correlation here, relationship studies. Only looking at the effect of one variable on another variable. Now that can be helpful if we're doing kind of exploratory studies or something like that, but it's often not enough to be sure of the finding that we're looking for. To be more careful in a regression or in a correlational study, we would do what we would call a prediction study, a regression or a multiple linear regression. And analyses like that take the scores on one or more variable and they predict the other one other variable. Okay, so for example, if we had SAT score, we could use that to predict GPA. Another thing that's super nice with these regression analyses is it allows us to look at more than just the one variable, independent variable, and one dependent variable. We can include multiple variables in a model that predicts some other variable, and we can even include variables that we think are related to our dependent variable but not part of our study, like income or something like that. So let's take a look at an example of this. Let's answer the question, does higher school spending result in lower SAT scores? Okay. Let's talk about the data here for a second. The unit of analysis of these data is 1 per state. Okay, so we look at, for each of the 50 states, how much is spent per student, the dollars per student, what the salaries of teachers are in each of those 50 states, and what the teacher per pupil ratio is. Alright, what you see here is a correlation coefficient where we have variables in rows and variables in columns, and we calculate the coefficient of relationship with each one. And by definition, the ones that fall on this diagonal of the matrix are a perfect correlation because we're correlating with themselves. So expenditure correlates with expenditure perfectly. Alright, let's take a look at expenditure, speaking of. So, the amount of money that we spend per student in a state, on average, is positively and significantly related to the mean salary of teachers. That makes sense because the majority of our education dollar is spent on, you guessed it, teacher salaries. And we also see here this relationship between teacher per pupil ratio and expenditure. We see that as a negative relationship, still significant, pardon me. And then SAT, this is what we really want to focus in on. This idea that when we spend more, we get more negative results. It seems kind of counterintuitive. Let's take a closer look. Here's what the data look like. We've got expenditures per student from 3,000 up to 11,000, and we've got average SAT scores from 800 up to 1150. If you were to look at this relationship, you could see that there's a negative trend, just like it. It's not particularly strong, just over 0.35, but it is significant. So let's see what might be happening. One way to look at these data is to not look individually at expenditure and salary, expenditure and per pupil, expenditure and SAT score. We can actually, in a more sophisticated analysis, look at each of those things at the same time in a model that we've put together. So this model says, how well does teacher per pupil ratio, teacher salaries, and school expenditures predict the SAT score? Okay, and just those factors in a model come up with a correlation coefficient of 0.458. Not a very high correlation. Also, when we look at the r-squared, we would only say that there's about 21% of the variance in SAT score that's accountable for these three factors. That's the whole model that includes all of these three things. We can also take a look at the coefficients that show us what each one of these values taken together, whether it's significant in predicting SAT score or not, and what the size of the prediction is. Okay, so the first thing that we notice is expenditure versus SAT ratio. This relationship is no longer significant when we take these other factors into account. Okay, we're looking for values less than 0.05 in this significance column. So it turns out that none of these individual factors significantly are predicting SAT score. Okay, so already we have a contradictory finding to what was found with our bivariate correlation. Let's go a little bit deeper and let's add another variable that we think might be related to SAT score. Let's add, in a second model, eligibility for free and reduced price lunch. We use free and reduced price lunch eligibility as a proxy for student and family poverty, which we do know is associated with achievement. And so we've got the same findings that we had from the previous setting, where we have non-significant expenditures, non-significant teacher per pupil ratio, non-significant salary. Okay, now when we add a second model including percent eligibility for free and reduced price lunch, we see that our prediction of SAT score gets much better. Before we had 0.458 coefficient, now we have 0.908 once we include eligibility for free and reduced price lunch. Okay, and then we've improved our r-squared to 0.825, where 82% of the variance in the SAT score is accounted for by these four variables. Let's now take a look at the significance of the variables. Again, expenditures, not significant. Teacher per pupil ratio, also not significant. Salary, not significant. But check a look here. We have a highly significant relationship of eligibility for free and reduced price lunch predicting SAT score in a model that's highly significant. So let's take a look back at our data here. We see here in these last cases, these four cases over here, that we've got on average low achievement on the SAT, and we've got really high spending. It turns out that 3 of these states are California, Hawaii, and New York. And these are areas, these are states that have high concentrations of poverty in their city area, and because of that poverty, we tend to spend more money on the education in that area, and we also see these lower test scores. Okay, so in a lot of